Okay, thank you. It's a pleasure to be here. So we'll be talking about black holes. I'll give you first a short summary. So black holes were surprising objects that were found in general relativity, found by Schwarzschild, just a year after Einstein wrote his equations. And they've been very confusing objects. Almost everyone that thought about black holes got some things right, some things wrong. And probably when I talk to you about this, some things will be wrong. So Einstein, for example, thought that black holes did not exist. They could not exist, but he was wrong. And other people, like Chandrasekhar, realized that very heavy stars could collapse into black holes. I'll briefly go over this. And they are, in fact, unavoidable consequences of general relativity. Hawking realized that black holes are not black, and they emit some radiation as objects. They can even be red or white. And he also thought that they would make quantum mechanics incompatible with gravity, and that quantum mechanics would need to be modified. Research in string theory showed that black holes, as seen from the outside, are compatible or seem to be compatible with quantum mechanics. And in fact, there is an interesting relation between quantum mechanics and spacetime geometry. But we are not done. There are still several puzzles involving the interior and several questions we haven't understood. Okay, so let's start with some basic things. So you probably all heard of Galileo's principle of relativity, which says that an observer traveling with constant velocity observes the same laws of physics as someone at rest. So if you are traveling in a plane and you are bouncing a ball there, it's the same as bouncing the ball here on this auditorium. Regardless of, the auditorium could be stationary, it could be rotating around the Earth, it could be rotating around the sun. All of that's the same. So if you have there, we have the two observers. They both observe the same laws of physics. Now, special relativity is the same as Galileo's relativity, except that we put one more law of physics, which is that there is a maximum speed for signal propagation, and that is the speed of light. So that we promote to a law of physics, and that's the second thing we would like to incorporate, that Einstein wanted to incorporate. And so in particular, these two observers that are traveling in some laboratory, they both have to see the same speed of light. They both have to see the light going at the same speed. And naively, you would think that the first, that the observer that is moving will see the light going more slowly, right? If you don't think that, I'm not explaining this properly. But the surprising thing about Einstein relativity is that in order for the two observers to see the light going at the same speed, the observer both is a bit contracted, and also its clock runs a little bit slower. And thanks to these two facts, the observer that is moving can see the light going at the same speed. And that's indeed how nature seems to work. So if you have, you can do these experiments and find indeed that light moves at the same speed independently of how you're moving. Now this leads to the so-called twin paradox. So we have two twins, and if we take one of the twins and make it move far away, it will age a bit more slowly, because his clock will run a little more slowly. And when he comes back, he will be younger. Okay. Now, this twin paradox is sometimes confusing when you first hear about it, because what broke the symmetry between the two twins? Why are the two twins different? So the difference is that this one here felt some acceleration when he was accelerating out and when he was coming back. Okay. So in fact, let me propose the following question. Imagine that there is some rule that says that the twins are born, and when they meet again, they both die. Okay. Now, which of the twins would you rather be? The twin that was moving with constant velocity, or the twin that was moving with changing velocity? Okay. Yeah, you prefer to be the twin with constant velocity. Now, it turns out that elementary particles move this way. So this is somehow the reason why elementary particles move along straight lines and move with constant velocity if there is no outside influence. It's called the principle of least action or the principle of maximal proper time, okay? Leaving the biggest time around. And that's how particles decide where they are going to move in a space-time. They like to live as long as possible. So that's, we call it the principle of maximal experience time, or sometimes, okay, so what we learn from this is that space and time form a single entity, which is space-time. And the time we measure depends on how we are moving. But the reason we join space and time in a single word, space-time, is that depending on how two observers are moving, whether they're moving with relative velocity, they see different notions of time. They perceive different notions of time, but they both see the same whole object of space and time. An analogy that is sometimes made is that if I'm looking in this direction, I call this forwards and this to my right. But if I'm looking in that direction, I call that direction forwards and that one as time. And that observers that are moving are similarly labeling time and space in different ways than observers that are stationary. Okay, so now we're going to move to something that looks different, that well, has seemingly nothing to do with space-time. So we're going to talk about gravity. So Aristotle said that the heavier objects fall faster, while Galileo said that everything falls in the same way once we remove the effect of air resistance. Okay, if we were to drop two things from the Tower of Pisa, the two objects would fall exactly at the same time. This motivated, so maybe I should emphasize one more point here. So independently of the composition of the object, whether you throw a feather or a big rock, they both fall in the same way. So this led to Einstein's, what Einstein called his happy thought, which is the idea that when you are falling freely, gravity disappears. So if you were, he often used the idea of an elevator. So you are in an elevator and the elevator suddenly starts falling, then it would feel as if you are floating in space. So it feels as if gravity completely disappears. And he proposed this to a new law of physics, which is sometimes called the equivalence principle. So the idea that the force of gravity is such that when you are falling freely, it looks as if gravity disappears. So this in particular implies that the motion of objects with different chemical compositions and so on should be exactly the same. And this has been tested with great accuracy. When you have a spaceship and the astronaut, they're both falling in the gravitational field of the Earth, but they feel they are floating. Okay, so.
You meant a particle, you have an extension, it's not true.
What?
Must be elementary particle for that. If you have extension of positive gravity.
Yes, that's right. So this principle of equivalence, it only holds at very short distances. So if you are a big object, then you feel tidal forces. So that's, for example, the Earth when it goes around the sun. In principle, is not feeling the gravity of the sun according to this argument, but because the Earth is extended, there are some different portions of the Earth are pulled in different directions, and that's what creates the tides or tidal forces. And the whole theory of Einstein, well, it's related to what governs basically those tidal forces. There will be an equation on those tidal forces. So the idea is that those tidal forces are related to the curvature of space-time. So the idea of Einstein is that in order to incorporate this principle of equivalence, he proposed that gravity is due to the geometry of space-time. So the idea is that if you have a heavy object, it curves the space-time around it, and a particle, a small light particle, would follow a trajectory that would maximize its own lifetime. Okay, it will move in this curved space-time in a way that such that the lifetime is locally maximum. And in particular, something important is that when we talk about gravity and space-time geometry, it's important that that the flow of time is changed. So gravity changes the flow of time. So in particular, if we have a person on the top floor of the building and a person on the bottom floor of the building, then they will feel time going at different rates. So the person in the bottom floor of the building will see time going a little more slowly than the person at the top floor of the building. Okay. Now this is here I've greatly exaggerated this. So time flows more slowly, just a part in 10 to the 15. So very small amount, but it's an amount that can be measured. So people, scientists have constructed clocks that are precise enough to see a difference of 3 centimeters in height in the gravitational field of the Earth.
Here it's the pressure of the external force which you feel, right? So if you have free fall, you can make experiment to be really clean. Because it's not gravity which acts on you. You sit down, what you feel when you're sitting is the pressure of the magnetic force.
Yes.
But if in free fall, you cannot make this experiment that there is no gravity. So that's what it means, this experiment.
Well, this is an experiment you can make. So
But this is staying in the flow. The flow is under pressure from the flow. It's electromagnetic force acting on it, not gravity only. If you have pure gravity, how you can make this experiment with pure gravity? If you forget about other forces. Make experiment.
well, you need a clock. Yeah, so it's a good point. So in order to make any experiment, you typically need some physical system, some clock that is made out of.
He's supporting.
Yes.
You have pressure from there.
Yes. Yeah. So you need someone who keeps you at this location. So these are clocks that are not.
Fix this location.
Yes. So it's important that these clocks are not falling freely. And the Einstein theory of gravity makes prediction not only for things that are free falling, but also things that are not free falling. Like for us, we are not free falling; we are just being held by the floor. And the Einstein theory of gravity tells us that the clock at the bottom will go a little more slowly than the clock at the top. And that's a prediction that comes from the shape of the geometry in our neighborhood. So it's a property of the shape of the geometry of space-time around us.
So only you can measure it because there is extra forces. If I get electromagnetic
Yes.
forces,
Well, you have to have some way of keeping the clock at this location. If the clock was moving, if it was in orbit, for example,
therefore you cannot describe it to gravitation. Maybe
well,
electromagnetic
I mean, the clock could be in orbit, for example, and so then there will be two effects. One is that it is in orbit, it's moving. There will be a clock in another orbit, and then you'll have to sum the two effects. One is the motion of the clock, and so on, and you take everything into account. You find the right way the clocks are moving, and I don't know, for GPS, you need to find this out, for example. But this is certainly an experiment you can do. You get a prediction from GR that tells you how different the rate is, and it's been checked experimentally. Okay, so now we can have another version of the twin paradox, so where we take we do the same, but we put the twin near a massive body, and then the twin that stayed near the massive body would be a little younger. Now, when we talk about black holes and so on, the thing that Schwarzschild found was he found the geometry outside a massive body. So if you have a spherical massive object and you have vacuum in the exterior, he found the geometry in the exterior where you don't have mass. So for example, if you had a star, you have a star like we have here, he found the whole geometry outside, and in particular he found what the rate of flow of time was when you stay at a fixed position. As was emphasized just a moment ago, someone who stays at a fixed position here will have to be accelerating. So he would have to have a rocket that keeps him or her at that fixed position. Okay? So this person would feel some weight pushing him or her towards the surface of the star. Okay? Good. So now imagine that we have the same star and we make it smaller, so the same mass. So from outside we see the same mass, but we make the star a little smaller. So then when we make it a little smaller, the time would go a little more slowly. So this curve roughly represents how fast the clock is going here compared to a clock at infinity. Okay? And then the person here feels an even higher weight. And then it turns out that this geometry has the funny feature that there is a point, there is a radius, such that the rate of flow of these clocks goes to 0. So the clock seems to completely stop if you had a clock that sits at this position. Of course, to have a clock that sits at this position, one would have also to have a rocket that is super powerful, and the weight that this person would feel at this position would also be infinite. Okay. So that's what Einstein thought was weird, and that could not happen. So he thought that it could not happen to have this infinite slowdown of time. Okay. Now, it's important, as was emphasized a moment ago, that these clocks are not falling freely. They are being held by something, either a rocket or a shelf or something. And what would happen if the clocks were falling freely? So what would happen is that actually the geometry continues behind this surface that we now call the horizon. And we'll explain in a second why we call it the horizon. So if you continue beyond that point, so you can cross this point, you don't feel infinite forces there, so you just fall freely through there. And then you will end up, but the universe inside looks like basically like a collapsing universe. It's similar to a collapsing universe. And there will be a point in your future where the curvatures become very large, right? And the curvatures become so large that these tidal forces we were talking about before will pull from your head and your feet, and they will kill you. So that's not very good. So don't fall into the black hole, or don't fall from a ladder either. Now, okay, so a particle just falls fine through the through this horizon, and you go into the singularity. Now, once you cross this surface, you cannot come back out. In some sense, the interior of the black hole is really to the future of this surface. And if you cross this surface, then you cannot come back out for the same reason that you cannot come back out. You cannot come to the past. You cannot go to your past. Okay. But the important point is that you don't feel anything particularly special when you cross the horizon. But once you go in, you cannot avoid crashing into the singularity, which is like an end of time or a big crunch. Now, some analogy that is often given for this is to view. This is an analogy for explaining this concept of a horizon. That is some kind of imaginary surface. It's imaginary in the sense that there is nothing special happening at the surface when you cross it, but that is a surface that divides two regions of the space-time that cannot send signals from one to the other. So imagine you have a river. So we have some river here, and the water is coming to a waterfall, and the speed of the water is increasing as you go to the waterfall. Then if you have some fish over here in the river, if the fish can swim faster than the water, then they can avoid falling to the waterfall. But there will be a point where the speed of the water is equal to the maximum speed that the fish can swim, and then if the fish tries to swim, it will stay there. So that's the idea that time is frozen, let's say. That's analogous. And then if you go into the region where the velocity of the water is bigger, then you can't avoid falling into the singularity. So this is an analogy for the behavior of a black hole. And it explains the concept of a horizon. So in particular, if you had a fish swimming in this river and the fish cannot see the shore, they would not be able to notice that they crossed the horizon. Okay, so we learned a few things. Let me just summarize. So we learned that once you cross the horizon, you cannot get out. We learned another thing that was learned, and I mentioned it, but is that a very heavy star can collapse and form a black hole. And another thing that was learned was that there are objects in the sky that seem to be black holes. Now, since we are talking about black holes, let me just say a few words about real black holes, so the black holes that are thought to exist in the universe. And there are some that are produced by the collapse of very massive stars. They have a size of a few kilometers. And there are other class of black holes which are much bigger, that are at the center of the galaxies, that have sizes of the order of the size of the solar system. Now, how do you see black holes? The way you see black holes is that, according to this classical theory, black holes don't emit any radiation, so you can't see them. However, it might happen that there is matter around the black hole, and when matter falls into the black hole, it heats up, it becomes hot. It's roughly like, imagine everyone trying to rush out of this room, and everyone bumps into each other, starts shouting as they go out, right? That's roughly what happens with matter falling into a black hole. And what we see, and what we can see with telescopes and so on, is this light that is emitted from the matter collapsing into a black hole. And a more modern technique that we know we have, thanks to the LIGO detector, is that we can see the gravity waves that are produced when two black holes collide. So this is an example of a picture. These are real pictures of the very big black holes, so the black holes at the center of galaxies. This image here is an optical image of a galaxy, and these jets here are obtained from radio telescopes and represents particles that are emitted, are accelerated, and they emit radiation, radio radiation. And then you can zoom in and see a disk of stuff that is falling into the black hole. So the scale here is very big. The black hole here is, even though it's the size of the solar system, is smaller than a pixel in this picture. Okay. And many galaxies similar to ours have black holes like this at the center, and there is an effort going on now trying to image and trying to get a better image of the black hole that is at the center of our own galaxy.
What is the density of matter on such a distance to allow them interaction and radiation? So it's a pretty big distance, but a huge density. Where so much the energy matter comes there. It's more density. If you put all stars there, they will see more. It's 400 light years. So if you put all stars of our galaxy in this ball, then it's not interacting so electromagnetically. Why have such a big mutual interaction? Looks to me impossible. It's 400 light years, so it's matter interact there on this scale. So we see this
Yes. They are forming a disk, right? So they're a narrow disk.
At each distance from the horizon, matter starts interacting and radiating.
Oh, here is a very big distance, so 400 light years. There's
It's impossible. There is not enough matter in galaxy to feel it to become interacting one to another.
well, they form narrow disks, and the particles in the disk collide with each other.
It's a disk. They're not a ball. They're a disk.
Yes, a disk. Yeah.
They're not uniformly distributed. What makes it uniform?
Let him continue.
But you understand? You understand it?
Just let him continue.
So you have a lot to understand. Okay.
Well, the astrophysicists studied this process of matter collapsing into stars and forming structures. They typically form disks. That's why our galaxy has the shape of a disk. And similarly, when you lose energy, but you conserve angular momentum, and that's the reason you have a disk, basically. Well, the center is the place with the minimum gravitational potential. So it's where things would like to sink to the center, and that's where the black holes are. I think there are some reports of perhaps black holes that are not exactly at the center in some galaxies, but I don't know enough about those cases. I think it's not really known exactly how these black holes were formed, whether they were formed before the galaxy or together with the galaxy, or the details of the formation of the black hole are not completely understood. They seem to be associated to the formation of the galaxy because most big galaxies seems to have one. Most recently, I said that black holes can produce gravity waves when they fall into each other, and they are detected. And the shape of these gravity waves carries information about the space-time metric near the collision and near the place where they were colliding. And these shapes agree pretty well with the shapes predicted from general relativity. So these are tests of the geometry of the black hole very close to the horizon. Okay. So they are tested at distances that they are, in some way you could say that they are imaging the black hole at distances very close to the horizon, while the images we showed before were distances much bigger than the horizon, when we showed the picture of the galaxy. Okay, so that's all I was going to say about real black holes, the black holes that exist in nature. So now I'm going to move on to a more theoretical aspect of theoretical investigations. And I'll try to explain why black holes are what interesting questions there are about, theoretical questions there are about black holes. They're very interesting conceptual aspects, and I'll try to explain what they are. So first, let me explain some interesting properties of black holes just purely in the theory of Einstein, classical theory of general relativity. So the first one is that black holes are very universal objects in the sense that independently of how you form the black hole, the end result will be essentially the same. It would be characterized by a few parameters like the mass and the angular rotation velocity and in principle also the charge, but in practice black holes do not have very charge. And so independently of whether you make the black hole with a blue star, red star, yellow star, you will always get the same black hole, right? The same black hole. And stars can have all kinds of little things. It can have sunspots. It can have all complicated dynamics. When they make a black hole, they are very simple. Okay. Now, these three are all images of the sun, by the way. They're not different stars. Okay, so that was one simple thing about black holes. There is another interesting aspect of black holes. So suppose you collide two black holes, right? So when two black holes collide, they emit gravitational radiation. So that means that some of the energy of the initial black holes gets emitted into gravitational radiation. That means that the mass of the final black holes will be less than the mass of the initial black holes. Here I'm using the energy is equal to the mass. Well, I'm putting C equal to 1. So it's the formula of E equal to mc squared. So the mass of the black hole would be less than the initial ones. However, it turns out that the area has to be bigger. So the area of the horizon, so we can think about this horizon, and an interesting quantity is the area of the horizon. And the dynamics of these black hole collisions is fairly complicated, and only recently, let's say in the past 10 to 15 years, people managed to solve it with computers. Before there were computers, but they couldn't solve it on computers, and it was a breakthrough to manage to solve these equations on the computer. So they're complicated equations, but they have the simple property that the area always increases. So it's interesting when complicated equations have a simple property, it means that there is some simple law governing this. And so far we've discussed black holes according to Einstein's theory, which is a classical theory. And once we include quantum mechanics, we find the new surprise. And that's the fact that black holes might not be black. Okay. So what Hawking found was that when you consider quantum particles moving in the space-time produced by the black hole, that geometry that Schwarzschild found, the quantum effects imply that you have some radiation, and the temperature of this radiation increases as the size of the black hole decreases. So for astrophysical black holes, this temperature is very small. So if you had a black hole with the mass of the sun, which are the smallest types of black holes that are made by natural processes, at least known natural processes in our universe, this temperature is very tiny. So this temperature has not been seen in any of the real black holes. So it's a very tiny effect for the real black holes that have been made, that are produced in the universe. But in principle, you could imagine a smaller black hole. Would be harder to produce, but in principle, you could imagine it. And those black holes, if you had a black hole which is small enough, roughly the size of a bacterium, which is the wavelength of light, of visible light, then those black holes will look white. So they will look like a small white dot. Okay. They would be very heavy. They would have the mass of a continent. So they are not a nice flashlight. So now, let me briefly give you a little cartoon that's for this the creation of these particles. So this occurs in the theory. It's important for this to consider the theory of relativistic particles, so particles that obey the principles of special relativity. And in those quantum theories, the particles can be created and destroyed. And the vacuum in those theories is a kind of complicated object where particles are constantly being created and destroyed. But there is a kind of principle which says that you can have pairs of particles, one with positive energy and one with negative energy, and they can exist for a very short time. because there is a principle that says that energy should always be positive. But for a very short time, due to the Heisenberg's uncertainty principle, you can have a negative energy as long as it exists for a time which is very short, so that you cannot actually measure. Right? So it's a policeman sort of checking whether the energies are positive, but if the energy is negative for a very short time, the policeman cannot do anything about this. Okay. Okay. So in flat space, there is no net particle creation, but in the presence of the horizon, the same thing can happen. But due to the distortion of the flow of time, what is negative energy from the point of view of the outside, from the point of view of the inside policeman, is just a regular positive energy particle. So the inside policeman is perfectly fine with that particle, because his notion of energy is different, his time is flowing in a different way. And for that reason, when this pair creation process occurs, the positive energy particle can go all the way to infinity, while the negative energy goes into the interior of the black hole and decreases the mass of the black hole. And in this way, the black hole is losing energy by emitting this radiation. Now, so it means that as a black hole emits radiation, it will lose some mass, so it will have some finite lifetime. And the lifetimes of various black holes are like the following. So a black hole of the mass of the sun or the Earth will live much longer than the age of the universe. A black hole with an ordinary mass, let's say a mass of 100 kilograms, would evaporate in a tiny fraction of a second, so it would be worse than a nuclear bomb because all this mass would be converted into energy. And a black hole of a mass about a mountain that would live roughly the age of the universe. So if those black holes were created in the beginning of the universe, they would be evaporating right now. And in principle, there could be very small black holes producing particle accelerators, and they would decay very quickly. Now, none of these black holes have been seen in any of the particle accelerators that were built. Okay. Now, I should mention, well, I will discuss now some theoretical problems with black hole temperature, but I should mention in passing that even though Hawking radiation has not been seen for black holes, there is a very similar phenomenon in cosmology that I won't discuss in detail, that occurs when the universe expands very quickly, and there is a kind of cosmological horizon. And because there is, again, a kind of horizon, there is a temperature, and this temperature is believed to have created the initial perturbations in the structure of the universe. So in some sense, even though Hawking radiation was not seen in the context of black holes, there is a similar phenomenon that was seen in the context of cosmology, that we use to explain some aspects of cosmology. Okay, so now I'm going to start discussing these theoretical problems with the black hole temperature. So it creates some problems, and I'll discuss a bit what these problems are. So when we think about temperature, since the time of Boltzmann, we think in terms of the motion of the microscopic constituents of matter, right? So if a system is hotter, then its microscopic pieces are moving a little faster or a little more than if it is colder, okay? Now, there is an associated notion, which is the notion of entropy. So entropy is counting the number of possible states or possible arrangements of those molecules. For example, in the case of the gas that we had in the previous transparency, the number of configurations is this entropy. And the first law of thermodynamics gives us the entropy if we know the energy and the temperature. And if we apply this to black holes using the relationship between the mass and the temperature that Hawking had found, we find that the entropy is actually equal to the area divided by, well, in terms of the Newton constant and so on, and h bar. And when you put in what these numbers are, you find that it's the area divided by a very tiny distance, which is 10 to the minus 33 centimeters. So for a macroscopic black hole, which has a huge entropy, much bigger than the entropy of anything with the same area. But the fact that the area has an entropic, has an interpretation as an entropy, has puts an interesting, well, gives a new light on the area law that we discussed before, that was actually discovered before the discovery of Hawking radiation. It's also found by Hawking. So this area law can be interpreted as the second law of thermodynamics. The area law was the law that said that when black holes collide and so on, the area should increase. And so that's interpreted as the increase of the entropy. And that's the second law of thermodynamics, saying that the entropy should always increase. So it's consistent with the second law of thermodynamics. Notice that the Einstein's equations were just a classical equation. They didn't know anything about the laws of thermodynamics. So this is a very interesting connection between the laws of space-time dynamics and the laws of thermodynamics. Now, the question is, what are the constituents of a black hole? So we think that the heat and the temperature of the black hole and the entropy should come from the motion and there's some microscopic constituents, but what are they? And now, whatever they are, they should be basic constituents that depend only on space-time, not on the matter that forms space-time, because we saw that black holes were very universal. You could make black holes with matter. You could even make black holes with gravity waves. So in theory, if you focus a bunch of gravity waves into a small region, you could, in principle, make a black hole. Whatever the degrees of freedom of a black hole are, they should tell us something about the structure and nature of space-time itself. Now, a related issue is this problem of information loss. So we can form a black hole in different ways, but it always seems to evaporate in the same way, emitting radiation that has no information about what we send in. So we send in some information, but we get some thermal radiation, apparently with no information. And in quantum mechanics, so in any system that is governed by quantum mechanics, information cannot be destroyed. I mean, it can be hidden and can be stored in a complicated way, but it cannot be totally destroyed. An analogy is the following. Suppose I take a piece of paper and I write a letter, right? So that's some information. And then I take the piece of paper and I cut it in many small pieces, right? So then it will be hard to know what the letter was, but if you had enough patience, you could reconstruct what the letter was. The information is still there. Quantum mechanics does similar things with systems, so it's similar in that sense, that you cannot destroy the information. So there would be subtle differences in the outgoing radiation that carry the information of how the black hole was made. That should be true if quantum mechanics was correct. So in order to answer some of these questions, we need some theory that puts together quantum mechanics and gravity. And one such theory is string theory. And so I won't discuss exactly what string theory is. I'm going to say that it's a theory under construction, and it's a theory of quantum gravity. So the quantum mechanics is a theory of the quantum mechanics of space-time, and it reduces to Einstein's theory of gravity under ordinary circumstances. Ordinary mean of ordinary life, or ordinary things that happen in the universe. So that is low energies and long distances. And one aspect of string theory is that it can describe in a complete way certain simple universes with negative curvature. And I'm going to use this aspect to discuss some aspects, to discuss black holes. And this is something that we know by the name of holography. It's the idea that there are certain spacetimes that whose whole gravitational description and quantum gravity description we can give completely in terms of a theory that lives on the boundary. And on the boundary, we have a theory of very strongly interacting particles, but the particles on the boundary have no gravity. So in this way, we replace something we don't know exactly how to describe, like the theory of quantum gravity in the interior, by a simpler theory of strongly interacting particles on the boundary. So roughly, the picture is something like this. So you have two equivalent descriptions of the same thing. So you can have an object that moves in this space-time. These spacetimes look basically like a gravitational potential well, so that's why an object inside will somehow move as this yellow ball here. And that is represented on the boundary as the motion of strongly interacting particles on the boundary. So here, this random motion that I try to represent here is trying to represent the fact that the particles are interacting strongly. Now, in the same way that you describe a simple object, you can also describe a black hole. And black holes really correspond to a large number of a thermal system on the boundary with a large number of particles. Here, it should look more like a fluid on the boundary. I really ran out of patience making these little dots that were moving around. And so that's how we represent a black hole. And in particular, the temperature and entropy of the black hole are can be, well, are due to the motion of the particles on the boundary, and so you can compute the entropy or the temperature of the particles on the boundary, and it agrees with what you could compute using the gravity theory. I mean, this agreement can be done for some specific cases where you can compute both things at the same time. Yeah, it's important. The boundary is no, the boundary is at infinity. So these are some space. Let me go back. I went too quickly through this. The type of universes we can describe using this method are universes that have negative curvature. They are infinite in size. Okay, if you took one of those universes, you made a little map where each of these fish has the same proper size, and you project it onto the screen, you would get this map, right? So here the fish are are very small because of the effects of the projection. It's the same that happens when you take a map of the surface of the Earth and you put it on the plane. Then the pieces, let's say near the North Pole and South Pole, get stretched a lot. Here it's the other way around. These pieces get shrunk when you project them onto the screen. And so this boundary we're talking about is a surface very far away. If you imagine if we were living in this negatively curved space, we would take a celestial sphere, so some sphere very, very far away, and that's where the particles live. The black hole might be living here, but these particles live very far away. So the particles don't describe just the black hole. They describe both the whole interior geometry and the black hole in it.
The strong interaction comes from the density at the boundary.
Yeah, so in order for the interior to be described by Einstein gravity, you need particles whose interactions are large, and this is you postulate these interactions. So you have examples of universes like this, and then when the theory on the boundary is similar to the theories we have in nature. In particular, it's somewhat similar to the theory of the strong force, but with very strong interactions and a large number of colors, if you know what that means.
So you mean strong as in strong interaction, not necessarily.
Well, it's strong in the sense of the strong interaction, but also strong in terms of the strength of the interaction, so that if you cannot think of them as free particles, they are more in a complicated way. Now, here the important point is that the theory on the boundary obeys the rules of quantum mechanics, and then if you accept this relationship, then the black hole in the interior also obeys those laws of quantum mechanics. So this concept of holography is really a conjecture between different systems, and there is a lot of evidence that it is correct, but it's not proven. It's not proven mathematically. But if you accept it, then you can conclude that black holes are consistent with quantum mechanics. And so here I'm going to try to explain the same thing with an analogy. So I was asked a moment ago that whether the particles were at the surface of the black hole, and that sounded kind of reasonable. And I said that the particles were at infinity, and this sounds unreasonable. Okay, if it sounds reasonable, then I'm not explaining it clearly. So it's funny that we have these particles at the boundary at infinity, and then they are representing things that are happening in the interior, right? So out of the motion and interaction of these particles, we get a new dimension of space-time. So I'm going to try to explain how that could happen with an analogy, okay? How you can have this emergent geometry. And so it will be a verbal analogy. So we'll start with something simple. So imagine you have a sentence, like this is just some random sentence. So if a man does not keep pace with his companions, perhaps it is because he hears a different grammar, just a sentence. Now, when you hear the sentence, well, of course, you have a sequence of words, and you have a sequence of letters. You group the letters into words, and then when you analyze the sentence, you group groups of words into bigger grammatical structures, right? Some little clauses, and then there are the big clauses in the sentence, and then there are some correlations among the words in the sentence. So, for example, the word man and his and he are correlated, and the word, for example, keep pace is correlated with drummer. Okay, so there are all these correlations in the sentence, and all these correlations and deeper structure of the sentence was necessary for you to understand the sentence, and you did all this analysis in your head. Okay. But the idea is that this analysis that is done in at different layers is like an extra dimension, right? So here we're drawing it as a bit as an extra dimension. And so the analogy is that we could imagine the state of a quantum system on the boundary. So all these particles are in some quantum state, and it's let's say it's a one-dimensional quantum state. It lives along one dimension. It's a bit like the very complicated sentence. And this sentence has some structures, has some correlations. And the correlations at short distances are represented by these pieces of the geometry very close to the boundary, and longer distance and higher order correlations are deeper inside in the boundary. Okay. So this is the structure of the relationship. For those of you who know a little bit about deep learning and artificial intelligence, it's a similar story. So in particular, for example, the long distance correlations in the sentence can be represented by particles that move in the bulk and split and join in the bulk. Okay. So now the question is, what is a black hole in this space-time? So in this analogy, so let's imagine we have a well-formed sentence. So that would be analogous to something without a black hole. And let's imagine we start changing the sentence randomly. Okay. So here we made some random changes. They are here in a different color. So here we changed a few words. And in particular, these changes have destroyed some of the correlations that we had before. So for example, here we put its, and here we put she. So we drop some correlations. And the sentence makes a little less sense. Okay, so it makes a little less sense. So we can analyze this sentence up to a certain level, and then it stops making sense. So when it stops making sense, we say there is a horizon. Okay, so our understanding reaches some horizon, and because we lost those long-distance correlations. And then we can make more changes. So we can change more of these words, and then even the sub-clauses don't make sense. So we can say the horizon moved a little bit up. And then we can change everything. We can change all the letters, and then the horizon we moved all the way up. This doesn't make any sense at all. Okay. So now, the idea that a black hole grows and that the entropy increases and so on is the idea that if you take a well-formed sentence and you start making random changes, you are more likely to make it stop making sense and create disorder, and so your ignorance will grow. So changes are more likely to mess up a sentence if we edit it randomly. Now, on the other hand, imagine that these changes were made by an encryption process. So imagine that we took the original sentence and we changed it by some mechanism that, let's say, is known to us and produces this complicated thing. Now, this is the kind of thing your computers do when they want to send information through the internet, right? So if you want to send secret information that no one else will be able to figure out, then you encrypt the sentence and make it look random. And then if you don't know how you encrypted it, it looks random. So someone who doesn't know how you encrypted it would say there is this horizon. But if you know how to encrypt it, then we could reverse the process and recover the original sentence. Okay. Now the idea is that the laws of physics on the boundary, they change this quantum state, and it's analogous to an encryption process in the sense that it's reversible. So the laws of physics, the basic laws of physics, are reversible and are changing the quantum state on the boundary. And in principle, by reversing this process, we can undo the formation of a black hole, and in principle, recover the original information. Okay? So that's the analogy. So by having, the idea is that by having this theory of particles, which is subject to standard laws of physics, which are reversible, then in principle we can recover information. That's what it means to recover information, or to have a description that keeps the information explicit. Now another use for this relation of holography is to learn about strongly interacting theories, where the boundary theory would be the particles in our own spacetime, and the interior is some curved 5-dimensional universe. And that can transform complicated problems of theories of strongly interacting particles to simple problems in a 5-dimensional universe. So this is some other way of getting some information out of black holes. Now, an interesting, more recent development is some interesting connections between entanglement and geometry. So I discussed before I discussed the correlations of the state produce the geometry, and these correlations are quantum mechanical and are called entanglement. So entanglement is a kind of correlation that can exist in quantum theory. And I discussed how this in principle, well, I give a cartoon with the analogy of this verbal analogy to how it constructs the space-time. But it can change the geometry, so correlations can change the geometry in very interesting ways. And I will discuss here just one example. And this example goes back to the original black hole solution. So if you look at the original solution that Schwarzschild wrote, it's a solution that contains no matter anywhere. And it's really describing not one black hole, but two black holes. Two black holes that are joined through the interior, through some kind of wormhole. And so this is the simplest spherically symmetric solution of pure Einstein gravity with no matter. And the question is, how should we think about this solution? How should we interpret this solution? It took many years to understand that this is what the original solution was really saying. It took all the work of all those people in the right-hand side. So that solution can be interpreted as a wormhole. So you can think of this as two black holes that are far away, that are joined through the interior. Now, if you find two black holes in nature produced by gravitational collapse, they will have some matter inside, and they will not be equal to this solution. So I'm not saying that these are common. It's common to have these two black hole solutions. This is just a possibility. It's a possible solution. It's somehow a very simple solution, one of the simplest solutions of Einstein's equations, and we're trying to understand this better. Now, this is a wormhole, but it's not a traversable wormhole. So you cannot send the signal from one side to the other. So if you try to send the signal from one wormhole to the other, you cannot do that. So this is done. Yeah, I guess I should probably have explained. I'm running out of time. So, but these diagrams represent the causal structure of these two black holes. So here the vertical direction is time, and the horizontal direction is the radial direction. And they've been deformed in such a way that they can fit on the flat surface of the screen, and also where the speed of light corresponds to 45-degree lines. Okay, so if you are someone that lives here on the right side and tries to go to the other side, you cannot go faster than this 45-degree line, and so you go in, and then you end up in this red region, which is the singularity. So the outer diamonds here are the exterior of the black holes, and this triangle here is the interior, and this is the big crunch singularity inside the black hole. Okay, so you cannot go from one to the other. But we were saying that we can think of the black hole from the outside as some kind of quantum system, right? And each black hole has some set of states from the outside. Now, the idea is that wormhole that Schwarzschild originally found is really an entangled state of two black holes. It's a particular entangled state. So it's a state where the microstates of one black hole are correlated with the states of the other. Roughly speaking, imagine this picture of the gas that we had before. So we had a picture of a gas in a box. It would be like having two boxes of gas where the molecules are moving in exactly the same way in the two boxes. Okay, so if you look at only one box, they are moving randomly. They look like a thermal state. But if you look at both boxes at the same time, they're moving in a correlated way. So that's what an entangled state is. So let me again go back to an analogy, just to say in terms of an analogy. So imagine you have the same sentence we had before, but now we have it here in the bottom in a different language. Okay. So here, each of the letters is different. But if you start analyzing the sentence, it looks at a certain point, the meaning becomes the same, right? And then when you reach that level of analysis, both are exactly the same. So this is a case of two somehow correlated sentences. And then if you did this analysis, you would start seeing structure from shorter distances to longer distances. And at some point, you have some common structure, which is the middle line of this diagram. So that has the structure of the wormhole connecting the two black holes. Now, you can say, what does it mean to have this wormhole? What does it mean to have the wormhole if you cannot go from one side to the other? So, I will try to explain what it means by giving a story. So the story of Romeo and Juliet. Okay. So this is another version of the Romeo and Juliet story. It occurs far in the future, where these two young people, they like each other, but their families don't like each other. So they keep one here, and they send another one they send Juliet to the Andromeda galaxy far away. And but they are very smart, and they exchange entangled bits and so on, and they manage to create a pair of entangled black holes. Okay. And after they created the pair of entangled black holes, so here is Romeo's black hole, then we have Juliet's black hole over there, very far away. But they managed to create it in this perfectly entangled state. They are very resourceful, and they have access to a large amount of technology that we don't have access now. So after they do that, they jump into the respective black holes. And let's look here at the bottom part of the diagram. So they jump into their black holes, and their families that sit outside, they think they committed suicide. Okay? And the narrator of the story also thought that they committed suicide. Okay? But actually, what they see is something different. So let's go back. So we have this is the full space-time diagram of the black hole, of the pair of black holes. So each of them is, let's say when they are here, they are each outside their own black holes. They are separated by a long distance in the ambient space, but they are very close. They are very close in the through this wormhole. So they jump in, and in principle they meet inside. So they are close, and when they jump in, they meet inside. And in this version of the story, they just die. Okay, they meet for a while and they die. Okay, and from the outside point of view, if you look at each of the sites individually, there is no record of their meeting. Okay, so from the point of view of each of the families, they committed suicide and then never met each other. Now there is some small variation on this story where you can rescue Alice and Bob, but it's where you can rescue Romeo and Juliet. But I won't have time to discuss it today. So it doesn't have to end in death. They could be rescued, but it's more complicated. Now there are many questions about the black hole interior that we don't understand. So we know from the equivalence principle that if you fall freely through the black hole, it should look as there is no gravity and there is a smooth space-time there. And the mystery is how to describe the interior using the same variables that make quantum mechanics manifest for the outside observer. How to join together the picture of black holes that we get from general relativity and the picture of black holes that we expect from quantum mechanics. Okay, and that's part of the things we don't understand. So in conclusion, I hope I convey to you that black holes are fascinating objects where the geometry of space-time is deformed in a dramatic way. Black holes and quantum mechanics give rise to very interesting theoretical challenges. And string theory can describe black holes in a consistent way, at least from the outside. And space-time is an effective seems to be that space-time is an effective approximate concept that arises from more elementary particles living at the boundary of space-time. This is one picture we have for space-time. And entanglement plays a crucial role in determining the structure of space-time. Well, thank you.